All right, welcome to week 5. Ooh. Today I'm covering indexes and views. That should be a fairly short lecture. Then I'll discuss the tests that are coming down the pipe. Then I'll field any questions related to the tests, and that's what's going to happen today. I'm just going to go shut my door, and then we'll get going. It's just because it's quiet now. Give it 10 minutes, and then the gaggle will come down the hall again. Okay. Pat, and we go to here. All right. So, like I said, I'm talking about indexes and views. Apparently, you guys have already learned a little bit about views previously last term, which, as far as I knew, you didn't know anything about. So this makes my lecture even that much shorter. I'll just highlight some of the points specific to views. I'm going to start with indexes, though. Indexes are really important to help speed up database access. That's its purpose in life. When you normally run a query, and if there are no indexes, such as this setup here, select star from person where name's equal to Smith, what it does what's called a sequential scan. And a sequential scan means that it starts at record number 1. Then it does record number 2, number 3, and as it finds matches, it adds it to the result set. But until it finds all the matches, it'll scan the entire table all the way to the end. Now, if you only have 100 rows, even 1,000 rows, that's going to take no time. There is actually no benefit to an index. If you've got 10,000 rows, 10 million rows, 35 million rows, that's going to take a long time. It's going to read every single row and line by line by line. So one of the solutions is called an index. And it's called indexed file organizations. There's a couple of different ways indexes are set up. Essentially, what happens with indexes is that the records are stored either sequentially or out of order. When they're stored sequentially, it's known as an index table. An indexed table. That means the entire table maintains its structure itself. When it's not sequentially, it means the records are written anywhere. It's known as a heap table. It's like a heap of cats. You don't just throw them all in a pile, and who cares which one's on top, as long as you can pull the one you need out. Then what happens is you add on an external index to it, and that will retrieve data faster. An index is either a table or another data structure used to determine where the location of records are in a file. So that's the technical term for what its purpose is. A really good example is, now, every year I do this, the audience gets younger and younger, and I'm not. Anybody here remember card file systems? I think I've already used that example with you guys, right? If you go to the library, and you got to find something, and you can't use the computer, so you go up to the little boxes, and you open up the drawer, and you're trying to find crap in there, and it doesn't work, because you can't find anything. So what do you do then? You go ask the librarian, can you help me find books on this? And they go, what exactly are you after? They go, oh yeah, you'll want these 3 books. How did she know that? I have no idea. But they swear to God, they've memorized every single book in the library. An index is essentially what that does. The purpose of the index is to allow you to find stuff really, really fast. There's a couple of different kinds of indexes, but the most common one's known as a Btree Index. And the next couple of slides will discuss those. A few things you need to remember off the top of your head. When you create a primary key, it is always indexed. The database server will index the primary key automatically for you. So it always creates an index so that the primary key can be searched on quickly. You can also create indexes on any other fields, and you can have multi-column indexes, so you can search on name and phone number. So if that's a search you do regularly, where you search for part of a name and part of a phone number, you'd create basically a compound index, and those are known as secondary indexes or secondary keys. In here it discusses that there's non-unique keys. There's actually a place in the world for unique keys. Those aren't so common. You'd create a unique index when you want to enforce certain rules in your database. for example, the primary key is always unique, right? Why? Because you can't have two of the same primary key in the given table. However, let's just say you have a field called username. And you want to make sure that people don't put the same username in twice. Now, there's a couple of ways you could do it. You could do it programmatically. So in your application, you do a select star from users or select count from users where username is equal to whatever you just submitted. And then it returns 1 or 0 or more than 1 or 0. If it's 0, you can insert. If not, 1. That's cute and all, but not the ideal way of handling it. If you put a unique index on it, you'll do the insert, you'll get an error. Not allowed to put in a duplicate. The database server takes care of it. It's instant. As long as your code can handle exceptions, and hopefully by now you're learning how to handle exceptions. Try, catch, fail. I'm not sure what it is in Python, but in PHP, C, C#, it's try, catch, fail. Okay, fine. Try exception. In the other languages, we have one more thing. So we can try, we can catch, and then we can fail. So if the catch doesn't work, you can fail gracefully. So it's sort of like, you trip, you try to catch yourself, and it doesn't work. Your other hand stops you from hitting your face on the ground. Try, catch, fail. So if your code is handling the exceptions properly, you can use unique indexes to avoid duplicate data in your database. You don't want to put too many of those in there because sometimes, it adds overhead. Indexes can be expensive. All right, so I'll start with a Btree index, and this is a simple example. The next slide has a complex example. So what it does is it creates a plan. And what it does, it'll take the data that's in the table and start splitting it up, and it'll go down up to 4 levels. Some database servers actually allow more than 4 levels. And Btree, people have arguments about what Btree stands for. Some people say it stands for binary tree. Some people say it stands for best tree. I've actually heard both used. I prefer binary tree, but best tree works just fine depending whose information you're reading. So essentially, what it does, it branches it out. So let's say at first you have 2 names in the database, one that starts with A, one that starts with M. It'll actually leave that on the first leaf. Now you add 2 more names, one with A, one with B, one with M, and one with Z. What it'll do is on the first leaf, it'll create 2 branches. So A to M on one side, and then N to Z on the other side. So when you look at the name, it'll look at what the first letter of the name is. It'll determine where in the branch it is. And then it'll just keep branching and bringing it down. Now, this one here is a tree search. And it's very similar to what I was just describing. So if you look at the first node at the top, F, P, and Z, so it created everything F and above, everything between F and Z goes into P, and then Z, from P to Z goes to the end. And as you search for things that start with A or B, it'll go into this leaf, and then it'll go down. So it breaks it down into little piles. If somebody wants a really technical explanation of this, I can provide it separately. Yeah. No, because it's B and everything before B. Then you got C and D, E and F. And if you end up with, A, like Aaron, Adam, and something else, what will happen then is, depending how many entries are in the B column here, it'll actually split those into another leaf further down. Like I said, depth of 4. B trees go to 4 levels of depth. Like I said, some database servers will actually go down to 6. Oracle and Postgres can handle layers of 6 depth in its B trees. They're known as enhanced B trees. That means it can break. Those usually you end up using on huge data stores, where you're storing, for example, every single name of people in Canada. And it's this big giant tree of names. And you end up with how many Daniels are there in Canada? Just a couple of us. So then you'd have all the Daniels, and then you start sticking on the last name. So you had all the Daniels that start with A, all the Daniels that start with B. And the B tree starts breaking it down further and further so that as you search, it goes, is it greater than or less than the first value? Oh, it's greater than. Okay, is it less than the next one? Okay, it must be in this branch. Goes down to that branch. Then it looks at, says, okay, now here's my 4 piles or 5 piles. Is it less than this? Oh, yes, it is. It jumps down to the correct branch. So the search time basically works with number of nodes it needs to jump for each of the matches. And essentially, of course, as usual, everything on this side ends up being found faster than everything on this side. But it's only a function of the tests at the top. Right? So at this point, it's 3 tests. Is it this, this, or this? And then the jump comes down to 3 again, 3 again. In this case, it could be more like, 20 at the top, 20, 20, 20, and then 20, 20, 20 below. It just, the search time is, 1 layer plus n of depth. So realistically, what kind of difference does it make to you for performance-wise? Thousandth of a second. And so you could do a search on a, for example, at work we had one table where one of the foreign keys was indexed. People were complaining that queries are running slow. They were right. They really sucked. Somewhere along the way, this table just grew and grew and grew, and people hadn't realized how bad it had gotten, where suddenly some of the entries in it, the volume went up really fast. And then they started doing searches on orders with 100 items in it. And we had, the results were, the web page was taking 4 minutes to load, 5 minutes to load, because it was just hammering the server. I created an index on that column because I realized there wasn't one. 4 seconds to load. Right? 4 minutes, 4 seconds. One index. How long did it take me to create the index? 15 seconds. How long did it take me to figure out that's what the problem was? Half an hour. But it's one of those things where we didn't realize way back when we designed this database that this particular structure would grow so massive. Poor, no, I can't say poor planning, but poor, what's the word I'm looking for? Revisiting. Going post-analysis, says the things still running the way they should, yes or no, and then, there should have been more of that. But that's how a Btree index works. All right. The syntax to create an index is pretty straightforward. Create index, like create table. You give it a name, just like when you do a create table, you give it a name. But then the syntax changes after that. You say you're going to create an index with that name on that table, and that's the column you're indexing. So this will create an index on person with that specifically it's indexing the names. And this will create a standard Btree index. There's a few other options you have for indexes. One's a hash index, where it takes the values and basically fingerprints it, and it stores a fingerprint. Are they better? Sort of. Those are the indexes you'll use on huge chunks of text instead. But you can't do substring searches on them. It's just for finding, exact strings. There's certain advantages. So this standard Btree index gets created here. All right. Here's a couple of others. You can do multiple attributes. So again, here this example double index, right? On person, age, and city. So that allows you to search on 2 fields. So the query planner. Do you guys know what the query planner is? No. All right. I guess I got to explain what the query planner is. When you type up your query and you hit run, the database server receives the query. It looks at components of your query and it figures out the best way to retrieve the data out of the database. That's known as the query planner. Did you guys learn a little bit about how compilers work? You compile your Python and things don't work, right? If you're actually compiling your Python instead of interpreting it. The compiler does something similar, looks at all the code, optimizes the loops, reduces it to bytecode, and go. What this does is it optimizes the best way to retrieve the data out of the database. Are there joins? Yes. What kind of joins are they? What are we joining on? It figures out the best path through the query to make it as fast as possible. As one of the steps of the query optimizer is, Oh, they're doing a where clause. Okay, do we have an index that matches exactly what's in the where clause? So in this case, if we did create this index and we go age 55 and city is equal to Seattle, it'll use that index. That means it'll search quickly for that combination of criteria. However, if you just do select star from person where city is equal to Seattle, it will not search quickly because it's not part of the two-part index. So when you create indexes, you have to be careful. Specifically, if you create really complex indexes, your query optimizer will not grab them. So what you end up wanting to do is you have to determine what the most common ways of pulling data out of that table is, and you create indexes based on that. Of course, when you create an index, it'll help with ranging also. So if you did something like this, it would search quickly for the age because it'll help with the range. Now, there's a question on here, why not create indexes on everything? And that's a loaded question. Indexes are expensive. Anybody here ever have to delegate work to someone? Now, somebody said, get this job done, so then you go talk to your subordinates and say, okay, you two guys do this, kind of thing. Or it's group work and you're the group leader and you said, okay, you do this and you do this and you do this. And now, what happens is you're basically being bottlenecked by the productivity of the individuals. So, for example, we have a table. Table is 10,000 rows. And we are going to insert a new row into that table. That means it needs to go modify any and all indexes attached to that table. So let's say we created indexes on every single column. This table has 10 columns. What happens? We do the initial write to the database. We update the primary key index. Then we update, now we're up to 11, every other index. So for adding a single row, you just did 11 write operations. But they're not just write operations. What's happening is for the index, it's got to find the right spot to put it in the index. Therefore, it's got to do a read, then a write. So suddenly we went from 11 operations to 21, 22, maybe more. So suddenly you're constantly hitting the disk. And the other catch is, let's say your table occupies 1 megabyte. Each index can occupy anywhere from 5 to 25% the size of the original table. So let's just say all our indexes are 256K. So our table is 1 meg. Each index is 256K. We have 10 indexes. 256 times 10 is 2.5 megabytes. Suddenly our indexes are actually bigger than the data. That's not good. It gets expensive. It's hungry. It uses up disk space. The I/O constantly slamming the disk. The query optimizer, you go do a search that says, select star from person where age between 25 and 28 and city is Seattle and name like Dave. At this point, let's say you create all these different indexes and combinations of indexes. The query optimizer will look at all these indexes and go, I don't know what you want anymore. So what it'll do is it'll grab the best guess. And often it'll be, what's the first index that matches the minimum requirement for this query? And that's not necessarily the best index. It'll grab the first one it thinks is going to do the job. Some database servers, such as Microsoft SQL Server, has fantastic index handling, and it'll normally pick the right one. Database servers like MySQL, your mileage may vary. If you're using something like Access, no. It's done before you ever get out of the gate. So why do you not create indexes on everything? It impacts performance. It can impact performance negatively. If you create indexes on, say, name and age, and you do those queries often, or name and city, or just you search the city all the time, you create a single index for that. Those are great. They'll work. If you create indexes on everything, you're just adding lots of write operations. So instead of taking 10,000th of a, say 10,000ths of a second to write the record to the database, you might be looking at a second. I know you're saying, what's a second? I'm sure Google cares about 1 second, so does Amazon. Because you know, for all those 100% performance loss, especially if you go, for 1,000th of a second up to 1 second, it's 100 times slower. Now imagine if every transaction on Amazon was 100 times slower than what you're experiencing now. Doesn't sound like much, but can you imagine the snowball effect? Where everything takes an extra second, and everything takes an extra second, and then you're delayed by a second, that means she's delayed by 2 seconds, which means he's delayed by 3 seconds. So at the end of the day, during peak hours, might be waiting 5 or 10 minutes for your please check out. That's why you don't create indexes on everything. Dangerous. Okay, the hash algorithm, which I spoke about earlier. It uses what's called division remainder to determine the record position. The records with the same position are grouped in lists. So what it does, it sorts out where things are in the record. And if it just so happens that if you have multiple things with flyers, it'll group them all together. So that way, all the flyers are in one set. So it's just a different pile. So instead of doing a nice Btree, it actually builds lists where things are instead. For some things, it's really good. For some things, it's not. As a rule of thumb, stick to your Btrees. Unless there's a specific reason why you want to use the hashed algorithm. And like I said, if you want the more technical explanations for these, I've got a textbook I can share with you that has like 10 pages of mumbo jumbo. But as a rule of thumb, stick to the Btrees. All right, unique and non-unique indexes. Unique indexes, they're done for primary keys, but you could use other unique fields. These guys have customer ID, which is a primary key. In this case, well, they're treating it as a primary key. But like I said earlier, you could create a unique key on a username, or you could create a unique key on an email address so that people can't insert an email address twice. It's a good way to keep your data nice and clean. Secondary indexes, there's for grouping entities. For example, you want to group by zip codes or by product categories, product descriptions. So one of the other perks of the index is when you're running aggregates. Do you guys remember what aggregates are? Did you learn about aggregates? Sum, count, min, max, average. And then you use a group by at the end. Well, the indexes will improve the performance of the aggregate functions because it understands how to group by the index. It groups by the index instead of the actual values. So instead of doing a table scan and group by city, and it actually scans, Seattle, Washington, Toronto, Vancouver. It'll actually say, oh, I'm going to index based on city index number A, index number B, index number C. And it'll actually speed up the aggregates that way. It's good. All right. Here's some basic rules for indexes. You want to use them on larger tables. And by larger tables, I mean, more than 1,000 rows. Less than 1,000 rows, you'll never see the difference. Obviously, you index the primary key of every table, and like I said earlier, most database servers index it automatically. Index search fields. In other words, fields you're going to find frequently in the where clause. If you search commonly by phone number, index the phone number. If you search commonly by postal code, index the postal code. If you search by name, index the name. If you will be doing order bys and group bys, you might want to contemplate indexing those, but often those are the ones you're searching on anyways. Because often you want to say count star, comma, city, from people, because you want to know how many people are in each city, where, city like Vancouver, whatever. Yeah. Yeah, they've indexed the dates. Well, they've indexed the dates so that the search results come in faster. And by the same token, often searching by newest, oldest, historical popularity, that kind of stuff is stats people like to search on anyways. Specifically, if you go to Reddit, you got hot, you got what's new, and then you search, you can say, how long things have been. Here they say index when there's more than 100 values, but not when there are less than 30. In other words, if there's less than 30 values, don't index. Honestly, I'm using the number 1,000. This is an older slide based on a really old textbook. This is a textbook the CST8250 students are using. But yeah, definitely index more than 1,000. Less than 1,000, 90% of the time the table's in memory anyways. And it's not going to get any faster than random memory access. But definitely if there's less than 30 rows, these would be reference tables like order status, country lists, that kind of thing. Okay, more rules. Avoid use of indexes for fields with long values. Why? Because the size of the index grows and grows and grows. Let's say you're indexing a field that's 1,000 characters. The index actually has the most significant, I gotta be careful how I word this, it stores the significant number of values to make that row unique inside the index. So let's say you're storing people's names. And I'll use my name again, Daniel. And we know for a fact that there's 25 Daniels in the database. There's 3 that start with G, 2 that start with GA, and then the rest of them are unique. So it would need to store in the index DANIEL space GA. And then the next. So it would need to store 9 characters to uniquely identify each of the records inside the index. So let's say you're storing huge amounts of text where the first part is very similar. Once upon a time, there was a princess, and everybody keeps writing the same story. But she wasn't really a princess; she was a prince. There suddenly it'll store up to there was once upon a time there was a princess, comma. It would store that into the index, and then the next word would be stored along with it, and therefore you're eating up tons of space. They say maybe you should compress the values first. That gets a little iffy, depending what kind of text searching you're trying to do. By compressing, they mean making a fingerprint of it, that kind of stuff. Or you want to just store the first 100 characters in a separate field and index that, so at least the first part is fast. If the key to index is used to determine the location of a record, use a sequence or a surrogate key. Use a synthetic key. So for example, you decided to use natural keys, and you guys remember how I felt about that last week, right? Don't use them. But let's say you're indexing natural keys and you're indexing a person's name, which is a really terrible index, by the way, to use that as a primary key. Instead of storing numbers, it's storing, for example, in my case, say 9 characters to uniquely identify me in the index. If you're using a number, B-trees of numbers are really, really fast. Because let's say you got 10,000 rows, it'll set up a tree. Is it greater than 1? Is it less than 5,000? Is it, 750 to 1,000 kind of thing? It'll do blocks. And when it's numbers, the matching is really fast because it's a number. Some database servers may have limits on how many indexes you can have, and some of them how many bytes can be indexed. That depends on how many fields. Modern database systems don't have very many limits, but some of the older ones do. Careful when you index attributes with null values. Some database servers do not recognize null values. That means that if you search for something and it hits nulls, it stops the index search at that point and breaks. Or things with nulls may not be indexed at all, so they may not even come up in a search result if it's depending on the index to find the records. So what it'll do is it'll index the table and go, finding, oh, I hit a null. Well, now we're going to do a table scan for the rest of this. So we might have done the first half of the table at a fast speed. It hits a table scan for the rest. Some database servers have gotten better. Oracle is now significantly better for handling nulls. It used to be terrible. Postgres handles them like a champ. MySQL, depending what table type you use. All right. That's indexes. But you know the most important part to remember? Index stuff that you're going to search on often and use the create index syntax. That's the two important things to take away from these slides. All right, now we're going to talk about views. Okay, views are relations, except they're not physically stored. So, you guys know what tables are, and apparently you sort of know what views are. Views are virtual tables. What you can use it for is to present different information to different users. For example, you have a table called employee, and there's a social security number, name, department, project, and salary. And let's just say that not everybody's allowed to see the people's social security number. Right? We're going to let the shifty guy that comes to work with holes in his pants look at your SSN. Good plan. So we'd create a view, and let's say we call this one developers. So what would happen is people that have access to view, the view called developers, would only see people's name and their project. So the employee's name and project. And only the people that work in development. That means that all you can see is the people you work with. On the other hand, people in payroll or HR would have access to the entire thing because they'd search from, they do select star from employee. So select star from developers. That way you can abstract your content. There's some advantages to views. And in a bit I'll talk about some of the disadvantages. But one of the big purposes of views is there's two purposes. One is to simplify complex queries. So you create a table, you have a query that joins 6 tables. And you know it's always going to be used regularly. You could create a view to store these somewhat more complex queries so that in the future you don't have to sit there and write out the whole thing again. You just go select star from orders where customer ID is equal to 5. And it would give you the customer's name, the order number, the order status, the shipping method with nice names, but this is all coming from joined up tables. It makes it simpler. Okay. As I said earlier, you can store your joins inside of it. So in theory, we create a view called Seattle View like that. You go select star from Seattle View, and it'll give you anybody who's in Seattle. At the same time, it'll grab the buyer and the seller of the product in the store from the purchase table and the other user. It looks like you're querying one table, but you're really pulling from 2. So it creates a virtual table. This is really old join syntax. I've tried to update all my slides to have the new one, but I guess I missed this one. So we got a Seattle view and we want to grab the products. So in theory, instead of joining 3 tables, we're joining a view and a table. Views behave just like tables. There are things you can do with it, which I'll explain in a bit, but that you can treat it like a regular query. Okay, now let's explain what's actually happening. So if we did a query that looks like this one, what the database server actually does, it takes this, translates it into this. So it takes this nice short query, which is select name and then the store from Seattle View, and it joins, I don't know why it says product, it should be saying purchase, but anyways. So it's joining up the products, and it filters it on shoes, and it'll convert it into a query that looks like this behind the scenes. So that's why it's called a virtual table. It grabs the initial query, figures out where your changes need to be, inserts them into the query, and runs the whole thing. It's basically compiling a query on the fly for you. All right. There's 2 kinds of views. There's virtual views, which is what you guys know as a standard view. Right? So you did a create view, blah, blah, blah. and it's used in databases, obviously. It's computed on demand. What that means is that it figures out how to run your view, runs it, returns the results to you. But it's always up to date because obviously it's doing it real time. There's something called materialized views, and different database servers handle these differently. They're used more in data warehousing. So for example, every night Amazon probably collects up the sales for the day, creates a materialized view, and dumps it somewhere else. And the purpose of them is that it takes the complex views that have many joins and returns it as a simplified data set, and you actually store a simplified data set in its own table. It's fast because it doesn't need to do all the joins. But the problem is that it can have what they call stale data because it's not executed real time. You're not doing a select star from the view. You're doing select star from a table that was populated maybe 2 hours ago. That means you might be missing 2 hours of data in the materialized view. Materialized views are used for data warehousing, in other words, for reporting at the end of the day. If you are trying to look at the sales trends for the last 6 months, for example, and you're dumping the data nightly so that you have simplified views where you have the product name and the quantity that they sold for that day. Then maybe, you know, the average sale price, because depending with Amazon, the prices can change through the day, just like Walmart. That's what materialized views are for. Now, depending on the database server, you can actually modify the data behind the view, but there's a few caveats. For example, we have a table called, again, the view from developers we had earlier, and we do insert into developers. Joe and his project is Optimizer. What it'll do is it'll create this query, and it won't put in the SSN, it won't put in the department, it won't put in his name, his salary, I mean, but it'll populate these two. So now, what do you think happens if the SSN is not allowed to be null? Query is going to fail. This view is never going to be able to insert into that table because the SSN is set as not null. So what you have to do is you have to create what's called updatable views, where all the columns that are part of the view must be able to be inserted and updated upon, and any columns not included in the view must be nullable. You can ignore usually the primary key if it's a synthetic key because it's auto-incrementing anyway, so it'll auto-generate its value. So that one is usually safe to ignore. But if you want to do updatable views, you have to make sure that any column that is not included in the view you're trying to insert or update against allows nulls in the columns that aren't included. Otherwise, it's just going to shit itself. And then we have something like this where it's a non-updatable view. The second we've got a complicated view where we have joins. We wouldn't be able to do it because in this case we might be missing some of the attributes. So what happens is it tries to do a two-part insert and it can't because it doesn't have all the bits and pieces that it needs. So this is a more complicated version of the previous slide. That's essentially what views are used for. Now I'm going to add on a few items, and I'm missing a slide. I guess I didn't hit save before I turned off my laptop yesterday. There are a few gotchas when it comes to views. Gotcha number 1. Views do not understand changes to the underlying table structure. For example, you have a customers table where you have a name field. So your view targets the name field. Your view's happy, it's happily chugging along, it's pulling out names to its heart's content, and then suddenly product manager says we don't want to store names as a whole anymore, we want to store first name, last name. So you drop the column name and you add a first name and a last name. Don't do it in that order, by the way, because you just lost all your names. Normally you'd add the two new columns, populate the new columns, and drop name. Now you go to select star from whatever the view is, and it hits Name. Name no longer exists at the back. You get basically a runtime error. Why? Because the view doesn't know the table structure changed. So views can be stale in its definition. One of the other gotchas with views is, depending on the database server, they don't always survive recovery from backups. For example, MySQL mangles views. Its backup utility, which you're supposed to use to back up your database, doesn't always back up the views properly. It'll break them. Good job, MySQL. Yeah, so you have to just be careful. That's part of the test plan. So if you have a really weird query as part of your view, it may get broken as part of the backup. Apparently in recent releases of MySQL, this problem has been reduced to almost nothing. But even as of 4 years ago, this was a common issue. So if you go work somewhere and they're using an older version of MySQL, their backup plan might not work. Just putting it out there. Those are the two big ones that you have to watch with views. Other than that, views are run real time. That means they're no faster than an existing query. You can't index a view. But the view will use the underlying indexes that you have created in the database. But you can't add indexes, which means if you're using them as part of a join, so you got select star from table, join a view, it's not going to necessarily know what indexes to use for performance reasons. Thus, the views get broken. The performance takes a hit because it doesn't know what to do with the data. Okay. Any questions about views or indexes before I move on? Like I said, this was going to be short because this is not a really big topic. But any questions about either of them? Going once? Let's put some pressure. Going twice? 2.5, 3 times. Okay. All right. That's the end of that. Now, to discuss what's coming down the pipe next week. I'm just going to turn on some lights. Good morning. Everybody's going blink, blink. Okay. Now, just going to make sure I'm still in frame here. Actually, I'm going to turn off the projector for the time being. It's causing my camera to lose it. Okay, so as you all know, or you should know, if you don't, you're finding out now. But if you've been paying attention to the calendar and to the modules in Canvas, next week is your first round of midterms assessments. You have 2 assessments, a practical and a theory. The theory is done in class, unless you've got other arrangements and you know who you are. The only time I take attendance is during the tests. Because at least if you're in class, I can watch if you're talking to the person next to you. I can't stop you from chat lining, but I can definitely stop you from talking. But if you're not physically in the room, there could be 3 of you sitting off in a pod somewhere having a conversation about what the best answer is. Therefore, I will be taking attendance next week. There'll be a sheet, and you're just going to sign it. And if you're not on that sheet and you don't have the prior arrangements, and you did the test, it's going to be assumed you weren't here, and therefore you cheated. That being said, the test is open book. So, cheating is a relative term here. Like with my tests, it's done on Canvas. It'll turn on at 6 o'clock sharp. It'll turn off at 8 o'clock sharp, except for those that have got arrangements. And Canvas allows me to do it student by student. So that means, if I've made arrangements with you, it will turn on and off at that time frame for you. Right now, it's sitting at 50 questions, multiple guess, and true-false. You will know your answers. You'll know if you got it right or not right within you hit save and submit. What should you study? Which is normally what the next question is. What should I study? The slides and the PDFs that are on Canvas. And if you didn't take good notes, you might want to rewatch some of the lectures. In other words, I'm covering everything up till this point. Here's the good news, though. Whatever is on this test will not be on the next test. The tests don't accumulate. There might be some questions from this on your final exam test, but once you've done this, that's it. So for, after this week, you don't need to think about this stuff again till the end. Yes? 2 midterms and a final exam. So the term's broken down into 3 chunks. And I timed it so that all your assessments are done before reading week, so you can go do reading week and not have to worry about any assessments. Right? I planned it that way. Now, the other part is the practical assessment. That one is done in lab. You're going to come to your lab section, so that sometimes you might need to ask me a question or two to clarify things. What is the practical assessment? It is essentially the kind of work you've done in lab till the first quarter of Lab 5. So you should be working on Lab 5 this week. Essentially, what's going to happen is I'm providing you with a document. It's on Canvas. It's going to be on Canvas. It's all on the computer. And you're going to provide me with 3 diagrams. A conceptual, actually I'm going to bring back the screen for a second so you know how the grading's broken down. A conceptual, logical, and a physical. I just want to make my window small enough so you can't see the actual rest of it where it tells you what you're supposed to work against. Just give me a moment. Okay. Oh, that's pretty good. It mostly fits on. Oh, now I got to turn off some lights. Okay. No? Not that. Apparently I can turn this one on, but I can't turn it off. Okay, let's turn everything off. Oh, really? Okay, there we go. We're playing Guess the Light Switch. All right. The points are broken down as follows. There's 3 diagrams. There's a conceptual, a logical, and a physical. Theoretically, this should be quite doable within the 2 hours. Now, the conceptual is worth 5 points, so it's not worth a lot. But it's still 5 points. And essentially, it's broken down as, A, you get 1 point if you gave me a diagram. Congratulations, you got 1 point right off the top. Those that have had me before know about Dan's free 1 points. 1 point if it's provided. 2 points if you cover all the major data points. And I take off half a point per mistake. So if you forgot something, it's half a point. And the diagram shows relations. In other words, you created all the big squares and you drew some lines between them. Okay. Next one's the logical diagram. You get a point if you provided a diagram. Again, the diagram covers all the major data objects. In other words, you didn't miss anything important. Primary keys are now defined. So in the conceptual, I don't care if you provide me with the primary keys. I just want you to identify how things are connected. So you remember when I was doing the diagram on the board and I just basically drew the boxes without any of the attributes? That's the first one. The second one, I want all the required attributes are present. In other words, everything that's been described as part of the work is there. And the primary keys are defined. And you've created the relations and you've defined the foreign keys. So if you guys remember, I'll do a little diagram on the board in a minute. The physical, that one's worth 10 points. The physical diagram is worth 15. Again, a point for providing me with the diagram. Primary keys are defined. You notice if you did it here, you should have it there. The points carry forward. All required columns are present with appropriate data types defined. In other words, if there's a price and you make it a varchar, you're going to lose half a point. Because prices are not character, they're numbers. And if, for those of you who are asking questions about Lab 4 and Lab 5, where, I was talking about a range of numbers, talk about numerics, that kind of stuff. And I spoke about that last week, I think. So you give us some data types. All relations are present with appropriate foreign keys. Now, 5 points for naming conventions. This is something I haven't nailed you guys on yet. When you start working in the real world, employers will give you a naming convention. They will ride your ass until you get it right. I am providing you the naming conventions in detail right on the assignment or the lab or whatever you want to call this. Oh, stop there. Okay. Everything is lowercase, no exceptions. Primary key is always called ID. Primary key is designed to be unique. Obviously, it's a primary key. Descriptor fields can be called name. You can call it whatever you want, but just as long as you stay consistent. So you don't call it customer name, product name, pet name. It's name. Table names are plural. Field names are singular. In other words, it's pets, not pet. It's planes, not plane. Foreign key names are the singular form of the parent table with ID appended. I've already provided these naming conventions to you guys earlier this term. For example, customer ID would refer to the primary key of ID of the customer's table. That's the naming convention. So there's 5 points for naming conventions. I'm taking off half a mark for each mistake. I guarantee, how many people are in here now? 10, 11, 12, 13, 14, 15, 16, 17, 18. So about 40. 10 are going to lose all 5 points. I'm not being pessimistic. I want you guys to prove me wrong. But historically, it's usually about 25% of people that don't. Because they rush through it and they don't take that time. And if you think about it, the physical diagram is 15 points, right? 33% of the points on the last one is the naming conventions. So in other words, you forget to name your primary keys, but you have all your naming conventions, you're still getting a higher percentage than the guy who did everything else but got it wrong. The naming conventions. This is a good time to force you guys to start thinking about the naming conventions as part of the work. Because that's what it's going to be like I said, when you go out there and you get your first job and they give you naming conventions, and then you decide to cowboy and do it your own way, and then they're going to come back and slap you in the back of the head a couple of times telling you what the heck do you think you're doing? Well, I'm giving you guys a virtual slap in the head. Essentially, if you want an idea of roughly what kind of stuff you're looking at, this is not an exact same example, but you do have and it showed up on this screen. Okay. This is a normalization exercise. It's not the same exercise as what you do, but you'd apply some of the same techniques. Obviously, you've got to figure out what the different data objects are. So as part of the process of figuring out your conceptual diagram, you might want to look at what's here and start figuring out the objects. This gives you a nice little fake-looking invoice. And it shows all the different normal forms. And at the end, it shows you a physical diagram. These normal forms help you break down what all the different objects would have been based on that invoice. So what I'd recommend for you guys is review this. And so you can think about how things are interconnected. That way, when it's time to do a conceptual diagram, which basically you can almost get away from the second normal form, you can start doing your conceptual. The third normal form would give you your logical, which at that point also gives you your physical. Because then, what's the difference between a logical and a physical? Many-to-many relationships have been resolved. In other words, you've created the linking tables, and you've assigned data types. That's the difference between logical and physical. Many is resolved, and you got physical data types. So the jump from logical to physical is very small. Okay. Now, the next question that usually follows is, what formats do I want them in? Okay, you can do it on pen and paper and take pictures and upload pictures. As long as I can read your handwriting. So if you try to get clever and use some really shitty handwriting to try to confuse me, if I can't read it, TFB. And if you don't know what TFB stands for, ask the person next to you. Okay? Or you can use Visio, which you all get it for free anyways with the college. Visio is great because it's got templates for that. You can use draw.io. You can use any of the diagramming tools. If you're doing the PowerPoint thing or the Word thing, it might be a little bit harder for you because they don't really do that very well. But theoretically you could. But in the end, I want pictures. So I want PNGs or JPEGs or whatever. Any questions? Yes, there's always a question. It's multiple guess. Multiple choice, true, false. No. No, because then you wouldn't get real-time results. If it's fill in the blank, I could be really anal retentive. Because I used to do tests with fill in the blanks. And then all the students hated it. And those of them that have had my hybrids historically from a different program have experienced Dan's fill in the blanks, where if you don't type it in exactly the way Blackboard expects it, it gives you a 0, which I learned to really detest. So I've discovered to make things multiple choice, multiple answer, and true false. So true and false, you know what it is. Multiple choice, you know what it is. Multiple answer is select all that apply. So you're given 3 or 4 or 5 choices, and you've got to pick the ones that are actually correct. And be careful, because it's open book. I may have made some of the wording a little tricky, where you might have 2 answers that sound almost exactly the same, unless you know what you're doing, or you know how to look up the answer. The other thing about this test is half the questions are mine, half the questions are from previous teachers that taught this course. I took some of their questions and brought them forward. It uses the same terminology I taught, but it applies slightly different wording, which means it's not going to be Dan's wording you're used to hearing. It will be wording that makes sense, and the questions make sense based on the wording. But if you understand the concepts by rereading the PDFs and rechecking the slideshows, you should be fine. Why did I choose to do that? I wanted to make sure that I carried some of the history of this course along with me, so that when you have to go and do something else related to this course, if you've been assessed similarly to previous students, it's a fair way of doing it. So it's a 50-50 crapshoot on the questions. You'll know which ones are mine. They'll be pretty obvious. And you'll know which ones aren't mine because they'll have terrible grammar. Whoever wrote those questions had horrible grammar. But the answers are clear and obvious. So, well, clear and obvious if you know your material. All right, any other questions? You'll have something that looks similar to this. Perhaps a slight hair more complicated. Just a tiny little bit more complicated. So, like any assessment, you should strategize how you're going to go through it. You've got 2 hours to do it. Therefore, the conceptual, you might want to say spend 15 minutes, 20 minutes on the conceptual, half an hour on the logical, The physical shouldn't take much longer because you've got most of the stuff. It's just a case of retyping it in. Or depending what design tool you're using, if like you're using draw.io, you're just going to start filling in the data types. Just depending what approach you want to use to actually, you know, do your work. But yeah, that's, you know, you want to strategize. You got 2 hours to do it. Realistically, it'll take, you know, there's like a curve, right? A completion curve where I'd say 20% will be done in the first hour, and then, you know, there'll be this, and then there'll be the people who are here right till the end. Obviously, there's people that have a lab right before the lecture, and I really do feel bad for you because, well, you got 2 tests back to back. So what I'm going to do for that is I'm going to stick around in that other classroom to the last possible minute, and then I'm going to run here. And then, you know, be here for that assessment. Theoretically, there should only be a gap of about 3-4 minutes between the two. A little bit of it. So it'll cover everything that we covered till today. So does it include today's slides? Yes. How many questions are on views and indexes? 3? 4? I don't remember off the top of my head exactly, but it's, you know, a small amount, less than 10%. How many are on questions that have to do with primary keys, or what you use this kind of diagram for, or you know, what is a logical diagram as opposed to a physical diagram, that kind of stuff. Those are the kinds of questions you can expect. And like I said, they're multiple guess. So law of averages says you could theoretically guess through every question and still possibly pass. I don't recommend do that, though. Don't do that. Study a little bit first. So I believe that should be it. Any more questions? Going once, going twice. All right. Oh, one more. Okay. I'm pretty sure I said 50. I might be wrong. Hang on. No, I lied. It's 30. It's 30. It used to be 50, but they had a bunch of questions from SQL that you guys covered last term. Like they literally had, how do you select a record where the name is equal to this, and here are the fields? No, I took them out. No, well, no, it's not that. It's adding noise. I don't believe assessing on stuff that you haven't learned in the term. So I took out those assessment questions. That's why there was actually literally 20 questions that had nothing to do with the first third of this term. And they had nothing to do with the second term of this term. It was all on stuff you learned previous term. So I took those out. So the test is only 30 questions. It's not even 50, it's 30. So that should take all of 15 minutes, right? People are going, no. Actually, I bet I should time it. I bet you somebody will be done in 11 minutes. I mean, I had somebody go through a 200-question exam in 46 minutes. So, you know, it's theoretically possible. Believe it or not, they didn't do the worst.